So what is a vector subspace? A vector subspace starts with some vector space, so some set which has an addition and a scalar multiplication defined on it that satisfies all 10 of those axioms that we were looking at before. In particular, we have to be able to add two vectors and get another vector, and we have to be able to multiply vectors by scalars and get other vectors. And so that's a part of this vector space. But then a vector subspace refers to a subset. I think the book uses H here. So this is, in the beginning, it's just a subset. So it's just some smaller collection of elements of our vector space. But what makes it a subspace more than a subset is that the subset is also a vector space. Also a vector space. Under the same addition and scalar multiplication operations that the bigger vector space has. So anytime in an algebra setting, when the word sub, the prefix sub, is used, it tends to mean the same kind of thing, that we have a subset of something which has the same structure as that bigger something has. So we can do linear combinations in V, linear combinations, and in a vector subspace we can also do linear combinations. So that's the idea of what a vector subspace is. So looking at a concrete example for a moment, where our vector space is just the xy plane. So it's the set of all points x and y, where x and y are real numbers. Right. We also call this R2, or R squared, the two-dimensional real plane. And that's a vector space because how do you add in V? xy plus, let's say, x1, y1 plus x2, y2. How do you add two vectors in R2 in the standard way? Component-wise. You add the x components, and then you add the y components. By the way, when we've been working with these vectors in chapters 1 and 2, we've tended to write them as column vectors, so you can kind of keep that in the back of your mind as we're doing this. That how do we add two of these elements together? We add them component-wise. We add the first components, and we add the second components. The distinction between writing an element of a vector space as a column, as we've done over here, versus writing it a different way, as we're doing over here, that's a distinction we're going to work on in Chapter 4. Because, as we'll talk about starting tomorrow, I believe, writing your vector as a column vector is really writing what we would call coordinates of these elements, compared to just writing the elements themselves. And there is a choice to be made in how to convert an element into its coordinates. And that choice is the choice of a basis for your vector space, which is something we'll start getting into tomorrow. So for the time being, though, we're going to again consider these to be the same thing, and to blur that distinction as long as we can get away with blurring it. So either way we look at it, though, we know how to add two elements of this vector space together, and we know how to multiply by a scalar. And when I say scalar, I mean a single real number chosen from the set of real numbers. So how do you multiply a vector by a scalar? Again, component-wise. So c times x, comma c times y. So all in all, I mean, all we've done here is we've just defined addition and scalar multiplication. And if we were being completely brutal about the concept of vector spaces, we would have to verify that this addition and this scalar multiplication satisfy the conditions, 1 through 10. But really, let's just proceed on the assumption that those conditions are all satisfied, because they all are relatively obvious things when addition and scalar multiplication are obvious things. Things like the commutativity of the addition operation follows just from the fact that addition of real numbers is commutative. So if I trade places with these two vectors, then I get the same answer that I had before. So those properties are going to follow from the corresponding properties that real numbers have. So we're not going to dwell on that. What I'd like to do is to define a subset of this vector space and ask whether that subset is in fact a vector subspace or not. So let me clear out some space down here. And let's take the following subset. So my subset is going to be a set of points x comma y such that y is equal to x squared. So this is a subset of V. In particular, it's a subset that if my vector space V is this xy plane up here, then what does a subset H look like? The set of points where y is equal to x squared. It's a parabola. I'm going to be not particularly careful in what that parabola looks like, but it's something like that. So there's H as a subset of V. And the question is H a vector subspace of V or not? So when Ley makes this definition in the book, he takes this contention right here, that H is itself a vector space, and he breaks it apart into three important bullet points. What were those three important bullet points? The zero vector of V must belong to H. Okay.
H is closed under vector addition. That is, for each U and V and H, the sum U plus V is in H.
Okay, so I have to be able to add any two elements of H and get an element of H, and
then H is closed under multiplication by scalars.
Closed under scalar multiplication. Right. So I have to be able to multiply any element of H by a scalar and get another element of H. Okay. So these two closure properties are the ones that take usually the most work to verify. But let's take these 3 points one at a time and figure out which ones of them are satisfied by this particular subset. So first of all, what is the zero vector of our vector space, R2? What does it look like? First of all, what is it that characterizes a zero vector? What makes a zero vector a zero vector? It's zero, but what does zero mean? How do you spot zero when you see it?
The origin?
Okay, it happens in our example to be the origin. The point 0, comma 0. Our zero vector is right here. Also happens that when we talk about coordinates, that all the coordinates will be 0 as well. But that takes a little more work to prove. That's going to follow from the linear independence of the elements of a basis when we talk about basis and coordinates in the next couple of classes. But what is it really that makes this a zero vector? What makes it a zero vector is that it's the additive identity in our vector space. In other words, any other vector that I have, let's call it V equals x comma y, that if I add the zero vector to it, what happens? Nothing. Exactly. That's what makes the zero vector, is that when I add it to any vector V, I get V back. It's the additive identity. Nothing happens to a vector when we add the zero vector to it. So that's how we know the zero vector is the zero vector. So if that's the zero vector of V, then our first question is, does the zero vector of V belong to our subset? Yes or no? It does. Just looking at the graph, we notice that the origin happens to be one of the points in our subset H. And looking at it from the point of view of the definition of H, is it true that 0, 0 belongs to this set? Well, how do we decide? We just have to decide whether or not this membership equation, y equals x squared, is satisfied by 0, 0. Well, is it? If our y is 0 and our x is 0, is it true that 0 is equal to 0 squared? Absolutely. So there's the algebraic verification that yes, the 0 vector of v belongs to our subset. So that one's good. That one's totally fine. By the way, it's a much more common occurrence to rule out a subset being a subspace by falsifying this, rather than to confirm that it's a vector space by confirming it. Because if it just so happens that the 0 vector does not belong to our subset, then what do we get to conclude immediately? It's not a subspace. We don't have a subspace. Because every vector space has a 0 vector, every vector subspace, because it has to be a vector space of its own, has to include that 0 vector too. So if your subset doesn't include the 0 vector, automatically you can say no, not a subspace. All right, so now comes the next property, which is closure under addition. How are we going to verify whether or not this set, H, is closed under addition or not? What is my burden of proof here? That's right. So I'm supposed to take two elements from my subset, H, so 2 points on this parabola, if you like, and add them together. And if H is really a vector subspace, where is their sum supposed to live? On H, again. Let's do it geometrically first. So here I'm taking one vector v, let's call it v1 or something, and another vector v2, each of which is an element of H. It's a point on my parabola. And then I'm going to add these vectors together. But if I add this v1 and this v2 together, what's the picture that that makes? If you add two vectors, geometrically, what does it look like? There's the old parallelogram method of addition happening here. And so the sum of v1 plus v2 is this vector right here. Take away our parallelogram line so we can see that a little better. So there's v1 plus v2. Absolutely. So geometrically, what can we conclude? Does v1 plus v2 belong to H? No. If we add 2 points that are in this parabola, we get a point, in general, we get a point which does not lie on that parabola. So, to finish this sentence up here, v1 plus v2 does not belong to H, even though v1 and v2 themselves did. And that's a red flag. Oops. Cross that out there. v1 belonged to H, v2 belonged to H, but their sum did not belong to H. Therefore, this second condition, the condition that our subset be closed under the addition operation in our vector space, is not satisfied. And because that condition is not satisfied, we immediately have our answer on whether or not our vector subset here, H, is a subspace. The answer is no. And that's a geometric verification. That picture, I think, is very powerful. But we should probably also have an algebraic verification. Because not everyone is convinced by geometry. I happen to be convinced by geometry very often, but let's make ourselves some room here and sort out the...
So you say H is not a subspace?
That's right. H is not a subspace of V. I should probably make that a complete sentence. H is not a subspace of the vector space V. There we go. So what's the algebraic proof? if I wanted to prove that this subset is not closed under addition, I should take two elements of H and then add them together, and then explicitly show that it's possible for that sum not to belong to H. So here's one way to do that. If both V1 and V2 are elements of H, then what do they look like? Let's say V1 has an x-coordinate of x1. What is the y-coordinate of V1 going to be? If this is x1, then what's this? If V1 belongs to H. x1 squared. Belonging to H means that the y-coordinate is the square of your x-coordinate. So, an arbitrarily chosen point in H we could write as x1 comma x1 squared. And that would be the coordinates of this arbitrary point, arbitrary vector v, v1 rather. And then likewise, v2 should also be arbitrary and should in general be different from v1, so let's call the x-coordinate x2. And then the y-coordinate would have to be the square of the x-coordinate. Again, that happens because each of v1 and v2 belong to H. So the y-coordinate is the square of the x-coordinate. So now we add these vectors together. And when we add these vectors together, and again, that addition is coming from the addition in our vector space R2, in our bigger vector space V. We're using the same operation on our subset as we use on the larger vector space, which means we're just adding these coordinate by coordinate. So the x-coordinate is going to be x1 plus x2, and the y-coordinate is x1 squared plus x2 squared. And then the question we have to answer is it true that that belongs to H? So how do we know if a vector belongs to H? We have to know if it satisfies this condition of membership, if its y-coordinate is equal to the square of its x-coordinate. And is that true for our purple sum over here? So this is our y, this is our x. And I just want to know, is it true that x squared is equal to y? Well, x squared is x1 plus x2, the quantity, squared. It's the freshman's dream, exactly. Whereas y is x1 squared plus x2 squared. Are those the same thing? In general, no. Because if we expand out the one on the left, we get x1 squared plus x2 squared, but we also get the cross terms, 2x1, x2. So that demonstrates that this sum, in general, does not belong to H, because the square of x1 plus x2 is not always the same thing as the square of x1 plus the square of x2. And that's a proof that this set is not closed under addition. But it's also a little bit heavy-handed. This is the advice I remember giving to my abstract algebra students repeatedly. And that is, if we're trying to prove that this statement is false, that this set is not closed under addition, it suffices to come up with a single counterexample, rather than proving it in general. And this people tend to find a lot simpler to do. So rather than being completely arbitrary about these vectors, being arbitrary is good when we're trying to show that a set is closed under addition, because then it has to be true for every point in H. But in order to falsify that statement, we just need to show that it's not true for a single choice of points in H. So what I'm going to do instead of being completely arbitrary in my choices of V1 and V2, let's be completely specific. Let's pick a pair of points that belong to H, and then show that their sum does not belong to H. So give me an example of a point which lies on this parabola. Any point. How about 2, 4? That belongs to h because 4 is equal to 2 squared. That's one of the points that lies on this parabola. And again, because my parabola was kind of drawn half-heartedly here, might not exactly line up with the coordinate system on that graph, but we can say 2, 4 is an example of a point on this parabola. What's another example of a point on this graph? We could use 2, 4 again. Let's do something else. How about negative 1, 1? So that's a point over here. Negative 1, 1. So both of those points belong to h. Now let's add them together. 2 plus negative 1 and 4 plus 1, 1, 5. How do I know that 1, 5 does not belong to h? Why isn't 1, 5 an element of h? Because 5 is not equal to 1 squared. Exactly. So 1 squared is not equal to 5. So this does not belong to h.